Okay, so welcome to the first Optima seminar for 2024. I'm Rob Heinemann, one of the CIs of Optima and a professor in the Monash Business School. And today our speaker is Dr. Xiaoqian Wang. So Xiaoqian did her PhD at Beihang University under the supervision of Yanfei Kang, who was herself a PhD student of Optima director Kate Smith-Miles. So she has very good pedigree. And she is currently a postdoc working in the Monash Business School with me on the topic of forecast reconciliation and other things to do with forecasting. And today she's going to talk about optimal forecast reconciliation with time series selection. So I'll hand over to Xiaoqian. Thank you.
Thank you. And thank you, Rob, for your kind introduction. So I don't need to do that myself. And thanks for having me. It's really great for me to have the chance to speak at Optima. Today, I'm going to give a talk on optimal forecast reconciliation with time series selection. It's a work in collaboration with my boss, Rob Heinemann, and Shankar Vikram-Surya. For this talk, it will mainly have 6 parts. So first, I will give you an example to show what hierarchical time series look like, then followed by a definition of forecast reconciliation and a recap of reconciliation methods. For the third part, I will introduce the forecast reconciliation methods we proposed to deal with time series selection during the reconciliation process. And then I will pick up some simulation experiments and applications to demonstrate the results and the performance of our approach. And finally, some takeaway points will be given. So first, we will have an example. So the example data is Australia labor force data, which is released by Australian Bureau of Statistics. So the dataset comprises monthly data on the number of unemployed persons in Australia. Except for the total unemployment, we also have the data for each state and territory. And for each state or territory, we also have 6 different groups of job search duration. So if we focus on the bottom left node, this time series will represent the monthly series on the number of unemployed persons in South Australia with less than 1 month job search. So if we complete the whole structure, it can be considered as a hierarchical time series. Now let's have a look at the data. The top panel shows the total unemployment data in Australia. So it shows strong seasonality with prominent peaks occurring every January and lower peaks occurring every July. So for January, potentially it can be attributable to school leavers, and for July, it's the start of the financial year. And after COVID, we can see there's a prominent increase after 2020 and a prominent recovery after 2021. Then we have show other time series in the hierarchy. So let's focus on the bottom left panel. It shows the breakdown of the unemployment data by state and territory, while the bottom right panel shows the breakdown by job search duration. So both panels can show us rich and diverse dynamics. And if we compare these 2 panels, we will find the time series in the right panel looks the seasonal patterns can be more consistent. So it should be more easy to forecast. And I didn't show the bottom level time series here because there are so many time series, so we can't put all of them in a plot. So we come to the definition. Hierarchical time series is a collection of time series that are linked together in an aggregation structure. well, a grouped time series doesn't naturally aggregate or disaggregate in a unique manner. So for the Australia labor force data, we can disaggregate the total unemployment by attribute state and territory, and also by the attribute job search duration. And finally, for the bottom level series, it's a disaggregation by both attributes. To represent it mathematically, for any aggregation structure, we can construct an n by nb matrix S to describe the way the bottom level time series sum up. So for a vector of so BT is a vector is an nb dimensional vector of the most disaggregated observations at time t, and we use the summing matrix S to sum them up to get an n-dimensional vector of all observations at time t. So if we use this two-level hierarchy example, so we can construct the S matrix like this. For the first row, we sum up AX, AY, BX, and BY and get Y total. And for second row, AX and AY will sum up to A. And for third row, BX and BY will sum to YB, and so on. And this identity matrix is used to make sure the bottom level observations on the right-hand side of the equation will be same as itself on the left hand of the equation. So we will have a concept of coherence, which is a property that data adhere to aggregation constraints. So to forecast such a hierarchical time series, we have hierarchical forecasting. Naturally, the observations will adhere to all of these aggregation constraints. But if we come to forecasting, we can use any model to independently generate forecasts of all time series in the hierarchy. But in general, they will not sum up. So that means they are not coherent. So at this time, we need to impose some aggregation constraints on the forecasts to ensure coherence. And forecast reconciliation is a type of approach. It's a post-processing approach we can use to achieve this goal. And next, we will have a quick recap of linear forecast reconciliation. So now we only focus on linear forecast reconciliation. Suppose we ignore the aggregation constraints and we do forecasting and get all the forecasts of all time series in the hierarchy. And then we stack them in a vector in the same order as the observations. So we have Y hat, which is an n-dimensional vector of base forecasts at time t. Then we will use a G matrix to map the base forecast to a bottom level time series. So all the base forecasts are mapped to bottom level, and then summing matrix is used to sum them up to restore the hierarchy and to get the coherent forecasts of the whole hierarchical structure. Traditionally, we have a lot of single level approaches. The feature of these approaches will be they only select one level. So they use forecasts of that specific level to disaggregate or aggregate and get the forecast of all other levels. So for bottom-up approach, the G matrix will be like this. Only the columns corresponding to the bottom level series will be identity matrix and other columns will be 0. And for top-down approach, the G matrix will only have one column, one non-zero column, which is corresponding to the top level. And the column should be a set of proportions. So we can distribute the top level time series to the bottom level time series. Except for single level approaches, another popular reconciliation method is minimum trace reconciliation. It finds G matrix by minimizing the trace of the covariance matrix of reconciled forecast errors. So they will give a solution G, and the solution will only depend on the summing matrix S and the estimate of the variance covariance matrix of base forecast errors, which is W. There are so many different estimators of W, and here I listed 5 popular ones that has shown to perform well in both simulations and in practice. So for OLS estimate, it simply use an identity matrix, and for WLSS estimator, it only considers the structure of the hierarchy, and for WRSV, it considers the diagonal elements of the one-step in sample covariance matrix. And min-t directly use the one-step sample covariance, and the min-t shrinkage shrinks the sample covariance to a diagonal matrix. So the min-t approach can be reformulated as a least square problem like this, but we will have a linear equality constraint. If we focus on the estimate of W, we can get the intuition behind it. So the intuition would be the larger the estimated variance of the base forecast errors, the larger the range of adjustments allowed for forecast reconciliation. So for example, in a hierarchy, if we have a top level time series and it has a large estimated variance of the base forecast errors, then we can do a larger range of change on it for reconciliation purpose. That means the difference between the reconciled forecasts for the top level series and the base forecast for the top level series can have a large difference. Despite their benefits and the good performance, there are still some potential issues we need to address. First, because we have different estimates of W, and sometimes the most simply one, like OLS, and identity matrix works extremely well in some cases, but sometimes the complex version will work well. So if we use different estimates of W, it will give us very different results. So it's challenging to choose the right estimator of W. And the second issue is it's very normal that in a hierarchy, there will be some time series, they perform poorly. For example, the bottom level series, because the less apparent seasonality trend patterns or the large volatility. So in this case, because the G matrix will map all the base forecasts to bottom level, so it will deteriorate the performance of the reconciliation. And the third issue would be there are very limited research used in sample information for the forecast reconciliation. So to try to address these issues, we propose several forecast reconciliation methods with time series selection. Before we introduce these methods, we first explore one question: how can we achieve selection? So the purpose of this method is we want to eliminate or remove the negative effect of poorly performing time series on forecast reconciliation, which means we want to zero out some columns of G matrix. So when we map and sum up to get the whole reconciled forecast, we will not use any information from the poorly performing time series. But at the meantime, we don't want to zero out the corresponding rows of S. We want to remain S matrix as it is, because in this way, we can get reconciled forecasts for the whole hierarchy, including the time series we didn't use. So it's comparable to other reconciliation methods. If we look at this two-level hierarchy example, if time series A has poor forecasts, poor base forecasts, and we want to remove it, so we can just zero out the second columns of G matrix. And when we map the base forecast to bottom level, we will not use the information from YA. But at the meantime, we need to note that the other elements of the G matrix should be changed accordingly. So the first method we propose is regularized best subset selection, because it's very natural to achieve selection using best subset selection approach. So based on the min-t optimization problem, here we include two additional penalty terms. One is the L0 penalty. So lambda 0 controls the number of non-zero columns of G. And the other one is the L2 norm, which we can have some shrinkage. So including all of these penalties, we can achieve shrinkage and also sparsity. The addition of the second, so if we ignore the second penalty term, it becomes a best subset selection problem. But we include this penalty because this is motivated by some recent research. They suggested that the inclusion of this L2 penalty can improve the prediction performance of best subset selection approach, especially when the signal to noise ratio is very low. And here we also note that SGY hat can be rewritten as its vectorization form, and then using the Kronecker production and the vectorization to rewrite it again. So using such an equivalent equation, we can make it possible to solve the optimization problem. And then we rewrite it using a big M-based MIP formulation. So here we introduce binary variables Z and also a big M parameter M. So if ZG is 0, that means the columns of the matrix G, the jth column of the matrix G will become 0. But if it's not 0, that means the jth columns of G can take any appropriate values. So it's a very classical mixed integer quadratic programming problem, and we can solve it using some commercial MIP solvers. Here we use Groovy Python interface to solve it. And if we focus on the objective function, we will find we have two hyperparameters, lambda 0 and lambda 2. For lambda 2, we simply treat it and use a set of values that has a large range to as a candidate set. And for lambda 0, we first have a lambda 0, 1, which is the maximum candidate value of lambda 0. Here we replace SGY hat using astute benchmark method. So that's the reconciled forecast from the benchmark methods. It's used because we want to capture the scale of the objective function. And then we generate a grid of k values that decrease exponentially and along with 0. So we have the candidate set for lambda 0 and lambda 2, and we can do parameter tuning to get the optimal combination of them, which can minimize the in-sample sum of squared reconciled error. And then we have the second method, which is an intuition method. So instead of estimate the whole matrix G, here we assume S bar equals AS. And A is an diagonal matrix with diagonal elements being 0 or 1. And then we use the Minty solution directly and put S bar inside it, so we can get G bar. So in this case, the problem of estimating the whole matrix G becomes a problem of estimating a diagonal matrix A. So instead of controlling the columns of G, we only control the diagonal elements of A, make some of them to be 0. To make it more clear, I show an example here. So also we consider two-level hierarchy, and we use the estimate of W, which only considers the structure of hierarchy. So the Minty solution will be like this. Well, if we put the second diagonal elements of A as 0 and get the solution again, then the solution will become this. So when we compare these two matrices, we will find the second column of G is zeroed out, and then the elements of other columns are also changed. So it makes sense because the G matrix is used to map all the base forecasts to bottom level time series. So we can consider it as weights. If we remove the information of YA, for example, then the weights assigned to other nodes or other time series should also be changed accordingly. To solve the optimization problem for intuition method, we rewrite it as a mixed integer quadratic programming as well and solve it. So for parameter tuning, it's the same with the first approach. And for the third method, we consider group lasso approach with constraint. That's because we treat each column of G as a group. So there is a group structure among G matrix. And if we rewrite the Y minus SGY using the Kronecker product, so the group structure among G matrix can also be considered as a group structure among the X, which is the term inside the bracket. So it's a classical group lasso problem, but here we have an additional constraint for unbiasedness constraints. For the group lasso method, we also introduce WG, which is a penalty weight for each columns of G. So we can make, using this penalty weight, we can make it more flexible to deal with several hierarchy time series with different scales. And then to solve it, we rewrite it using second order Kohn programming formulation. So the last one constraint is a second order Kohn constraint, and solve it using Groby. So the penalty weights WG is set as this form. So we can consider the different scales of different levels. And for lambda sequence, it's almost the same with the previous methods, but except for the maximum candidate. So because when we ignore the unbiasedness constraint, it becomes a group lasso problem, and we can find the lambda 1, which is the smallest lambda value, such as all the predictors have 0 coefficients. That means for our problem, the solution of J will become 0. So it's an extreme case. So for now, our 3 methods we proposed under the assumption of unbiasedness for base forecast and reconciled forecasts. So in this case, the solution written by all of these 3 methods the solution G is at the non-zero columns of G should be at least equal to the number of time series at the bottom level, that is NB. So that means, for example, if we remove the A matrix, if we remove the A time series, the solution can remove the A time series, and we can still restore the full hierarchy using the observations from other nodes. But we cannot zero out or remove the information for both AA and AB, because in this case, we cannot restore the whole hierarchy using the observations of other nodes. So that's one of the property of the previous 3 methods. And finally, we here, instead of only consider the one step ahead forecast, we consider in sample information to perform the selection, which is empirical group lasso method. So because we consider in sample information, we don't need to have the unbiasedness constraint, and it becomes a classical group lasso problem. But instead of a vector y hat, here y becomes a matrix comprising observations from all time series on the training set. So for such a standard group lasso problem, we can solve it easily. And next, I will show some simulation experiments. Here we have two simulations. For the first one, the setup one, we wanted to use it to explore the effect of model misspecification. So here we generate the bottom level series using a structural time series model, and then we sum them up to get the data of the whole hierarchy. And here we consider a quarterly time series, and the length of the data will be 180, and the forecast horizon will be 16. And I will skip other details of the simulation. And the process will repeat 500 times, and so to ensure we can get stable results. So here, base forecasts, which is y hat, are generated using ETS models. And to examine or to explore the effect of model misspecification, we need to introduce some misspecification in some series. So we have several scenarios. Here I will only show one scenario in which we deteriorate the in-sample fitted values and out-of-sample base forecasts of series A. So our target will be removing out series A. That means the columns of G corresponding to series A. So this table shows the out-of-sample forecast results for this scenario. We show the average mean squared error for different levels, and also the average results for the whole hierarchy. And we consider different forecast horizons. And for the first row, base means the forecast results of base forecast. Here it's ETS forecast. And all the entries below shows the percentage increase or percentage decrease of the reconciled forecasts compared to the base forecast. So if the percentage is negative, which means it performs better than base forecast. If it's positive, it means it performs worse than base forecast. And the BU is bottom-up approach. And OLS, WRSS, WRSV, min-t, and min-t shrinkage means the min-t approach with different estimates of W. And the entries below the first row in each panel shows the results of our proposed methods using the corresponding estimate of W. And the E-min-t means empirical min-t approach, which also use in-sample information, but do not perform time series selection. And for the last row is the empirical lasso. That's the final approach we proposed. So if we look at the results, first we can say that the difference after we using our proposed methods, we can decrease the difference resulted by using different estimates of W. That's the first conclusion. And the second key point is for OLS, WRSS, and for OLS and WRS estimate, so this is an identity matrix for W, and this is a matrix only considering the structure. So for these two estimates, they are simple estimates. And for these two cases, our approach can achieve prominent improvement. But for the following three estimates, because they use the in-sample covariance, one-step in-sample covariance. For example, as I explained earlier, if the top level has large variance, then we can allow a large range of adjustments for it. So in this case, selection may be difficult. That's why the results is very similar to the benchmarks. And if we compare, for these results, our approach E-lasso and perform similarly to E-min-t, so no much difference. And then we look at the proportion of time series being selected in these 500 hierarchies. So for benchmark approach, they select all time series. But for our approach, our target, so time series A is expected to be removed. So when we look at the results, for some of them, time series A is being selected less frequently than others. So this matches to our expectation. But for some case, for example, for this one, the proportion of time series A being selected is not that low. That is because all of the bottom level time series are selected. So it becomes less important to select out the A time series because we can use the bottom level series to add them up. And then the final column shows stacked bar plots. So a darker subbar means a larger number of time series being selected in the hierarchy. So when we compare subset, intuitive, and lasso, we will find subset selection approach always give us less time series selected. And for simulation 2, we want to explore the effect of error correlation. So here we generate a bottom level time series using a VAR model and sum them up to get the whole hierarchy. And similarly, we repeat them 500 times and for each candidate correlation. So we consider a wide set of error correlation. And because our purpose is to select out some series, so we need to introduce some bias. So here for total A and BA series in the hierarchy, when we fit the model to get the base forecast, we will ignore the constant term to introduce a slight bias. But here shows an example of the simulated hierarchy, time series, and the residuals. So if we look at the residuals, we will find the slight bias has no significant impact on the base forecast. That's because the constant term is set as 1 here. So if we ignore constant term, it's relatively small compared to the data volatility. So it will be difficult to recognize this time series and select them out. So here, this table shows the RMSE across various error correlations. And also, our approach can reduce the difference resulting by using different estimate of W. And also for min-t and min-t shrinkage, for most of time, we give the same results as the benchmark. That means we didn't achieve selection. As I explained, it's difficult for this case to recognize them. And because we want to remove total A and BA out, so it's top A and BA, this one. So from the results, the 3 time series are also being selected less frequently than others. And then I will show the original example data, Australian labor force. So we have top level time series, and we have it's a grouped time series because we have 2 separate attributes. So for the bottom level time series, it's disaggregated by both duration and state and territory. So in total, we have 63 time series in this hierarchy, and we get the results of this data. So for intuitive and lasso, intuitive method and group lasso with constraint approach, for the most of the time, we get the similar results as the benchmark, as is their respective benchmarks. That's because for intuitive method, because we use the solution of min-t, so that means we include another one restrict constraint in the optimization problem. So it becomes difficult to zero out the diagonal elements of A. And for group lasso approach, because of the group lasso inherently will produce denser estimates. So that's why sometimes they will give us the similar results as the benchmarks. But for subset approach, for different estimates of it, we can achieve some improvement for different levels, and overall the improvement is not, sometimes it's not that significant, but there is some improvement. But surprisingly, for this application set, different from the simulation results, when we look at the empirical lasso, we will find there is a large improvement introduced by empirical lasso problem. And if we look at the number of time series being selected, we will find that for the empirical lasso, we only use 11 time series to do such a forecast reconciliation, but we can still get a great result. And if we look at ORS subset and WRS subset, we will find that if we compare duration and STT level, we will find more time series in STT level are being removed out. So we use more time series in duration level rather than in STT level. That's because when we observe the time series plot earlier, the time series with the duration level shows us more consistent patterns and should be easier to forecast. So that's why most of the time series in this level are remained. Okay, so to conclude the talk, first we propose 4 methods to achieve time series selection in forecast reconciliation. 3 methods we have unbiasedness constraint, and for 1 method we use only in sample information. And the results shows us that the subset selection approach and the empirical lasso approach are suggested because they can reduce the difference arising from using different estimate of W, and they perform well in both simulation data and application data. But we need to acknowledge that solving an L0 regularized regression problems with additional constraints remain a challenge. We noticed that there are several research recently published to solve the subset selection problem, but it's often in regression, in least squares regression context. So if we include additional constraints, it's still hard to solve it. So it takes a lot of time. Here are some selected references, and that's it. Thanks for listening.